of optical properties of amorphous molybdenum oxide for anti-reflection of metal conductors. My name is David Tsu from the Mackinac Technology Company. I'd like to acknowledge my co-authors, Matthias Müller from Fraunhofer, USA, Harald Kustenbauer, Christian Linke, and Joerg Winkler from Lansing. Before I get going, I'd like to acknowledge that my work has been sponsored by grants from ARPA-E. So the overview of my presentation, I want to briefly mention how I get started on molybdenum oxide in the background, briefly describe the sample preparation, how we solve for the optical constants, the N, refractive index, K, the extinction coefficient, from measurements of reflection and transmission. And from these measurements and this analysis, we can say some important things about the material, and then finally move over to the anti-reflection for metals. One of the main interests in molybdenum oxides is to make anti-reflection coatings to hide metal conductive lines in optical devices such as smartphones. A number of years ago, I met Joerg Winkler when he gave his presentation at the SVC in 2015. And at the end of his talk, I remember distinctly he expressed some frustration that perhaps the optical constants used in his modeling wasn't quite correct or quite right. And so I approached him and said, well, maybe I can help out making measurements for you. And a number of years later, we finally got going on a small project where I measured samples from him. So in this presentation, I will show you how we directly solve for the N and K of the samples from measurements of R and T. And we will, again, examine how we can use those to make anti-reflection layers for not only copper, but aluminum, silver, and gold. We made a number of samples over a range of target compositions from having stoichiometry of 2.0 all the way to 2.9, and in two different thicknesses, nominally 50 nanometers and 100 nanometers. Today I will discuss only the 50 nanometer films. The 100 nanometer films are for the most part, they're very similar, but subtle differences exist. Don't have too much time today to describe that work. All these samples were made under ambient temperature conditions, and therefore they will be amorphous, and absolutely no oxygen flow is in the sputtering, only argon. So the stoichiometry is solely dependent upon the target material. We first begin with showing you the reflectance of these samples. From 2.0, stoichiometry of 2.0 to 2.9, the reflectance becomes smaller, and we should know that that will mean that the refractive index will be smaller. So the higher the refractive index, the greater the reflectance. This is the transmission of the same samples. As the stoichiometry, as the oxygen increases from 2.0 to 2.9, the transmission increases. This will mean that the K, the extinction coefficient, is decreasing as we add more oxygen to our samples. Now, one of the things that one should be in the habit of is to look at the sum signal of R plus T, because this eliminates all effects of interference fringes. If you do it right and the sample is uniform enough, you should see no hint of residual interference fringes. And the point is that the absorptance can be seen as the difference between 1.0 and the actual signal here. I find this very instructive to get in the habit of looking at. Now, what we will do is take the geometry of one film on one substrate where we know the refractive index of the substrate, and we can express it as the complex refractive index n minus ik, which is the normal way to express the refractive index. And we should realize that the reflection and the transmission, which we can write down from various Fresnel equations, are extremely nonlinear in the refractive index of film and substrate. So what does that mean, nonlinearity? If it's linear, y equals mx plus b, there's only one solution. If it's a quadratic, there's two solutions. And if it's a trigonometric function like sine x, then there's infinite number of solutions. So because these are so nonlinear, we must expect that we will see more than one solution. So in this case, the substrate is a known. We have that because we have previously measured it. And the thickness will be an adjustable parameter. So we will find that we have very high fidelity to identify what the thickness is. And this is an example of the solutions that we've identified. It's important to understand, because of the multiple solutions, we will have one physical solution and many mathematically relevant solutions. So the mathematical branches, the greens, we can see they're all over the place. And mathematically, we don't require anything special. They don't have to be continuous across the wavelength range, but the physical branch, they must be continuous. The signal must be continuous, which is what this red line is. And we will find that it's the continuous as long as you selected the correct thickness. At this wavelength of 400 nanometers, there's a solution here, there's a solution here, there's a solution here, and here. Therefore, there's 4 solutions. So at every wavelength point that we measure, we expect to find more than one solution. Well, the continuity of the physical branch must be continuous. What happens if you use a thickness in your solution that is too thick? The P branch over here is nice, and all of a sudden it breaks apart over here. It's not continuous. On the other hand, if it's too thin, it breaks apart in another way. And you can see that this difference of 54.8 and 54.6, a difference of 0.2 nanometers, we know that this is incorrect. So previously we mentioned that the correct thickness was about 54.7 nanometers. And we are quite certain of that because of the continuity of the P branch. Now, when we put all of that together, this is what it looks like. As promised, the N is greater for low oxygen and becomes lower as oxygen increases, and the K becomes lower as the oxygen increases. Now, one of the things I will discuss about in a slide that is coming up shortly is what I call a trajectory of the N and the K. So I'm picking it at a certain wavelength. 550 is in the middle of our eye's sensitivity. And this trajectory kind of defines this material and defines how we made this material. I can imagine it might be possible that under different conditions, the lines, the data may not fall on this line. But in this case, we can see that there's a very high correlation to linearity, and this defines this material as it was made by sputtering. Now, so what we're going to do is to say, okay, suppose I have a material that is made at a stoichiometry of, say, 2.6, and I have that measured data. Can I go to the endpoints, 2.0 and 2.9, and combine them in a method say, a Brueggemann effective medium approximation, EMA? And can I vary this dial between phase of the 2.9 phase and the 2.0 phase? And can I recover the measured data of 2.6? And the answer is, for the most part, yes. The blue data, N and K, has been made by direct measurement, by direct solution of the R and T. And the green data is taking the endpoints at 2.0 and 2.9, varying the volume fractions, and you can see that the match is quite good. What this tells us is that molybdenum oxide, as we deposit it at ambient temperature, is a quite good mixture, atomically mixed assembly of molybdenum and oxygen atoms. Well, when we do that, we find that the stoichiometry of the film is slightly different from the stoichiometry of the target. Look at this slope, 0.973. It is slightly less than a slope of 1. 1 would be a one-to-one correlation, but it's slightly less. And what this means is that the film is slightly oxygen deficient in comparison to the target's stoichiometry. This is quite expected. Films never have the same stoichiometry as the target, and oxygen is usually lost slightly due to pumping from the system. So oxygen is usually a little bit deficient. So one of the things that is, now that we have the N and K, we can actually start analyzing things like, okay, what is the band gap of the material? And in order to quantify the band gap, we use the Taus method for quantifying the band gap. If any one of you have ever looked at the Taus method for the band gap, it usually involves, rather than the imaginary part of the dielectric function, it usually involves alpha. Problem is, alpha depends only on K, the extinction coefficient, and assumes that N, the refractive index, is constant, which is never true. So I encourage you to stop using alpha if you make bandgap calculations like this. Well, what does the data look like? There's two band gaps. There's one at higher energy and one at lower energy. The higher energy one is the typical bands due to bound transitions. And we have something quite interesting over here. This goes negative. This is real. A negative band gap is a property of semimetals. Just like if you plotted this up for graphite, which is a very famous semimetal, you would find a negative band gap energy. Well, this is a problem for doing optical analysis because while we have functions to describe bound transitions called Taus Lorentz curves functions, we have functions to describe free carriers of metals called Drude Lorentz functions, but we do not have functions to describe semimetals. So it's highly likely that some of the problems that Joerg discovered a number of years ago relates to the fact that this metal oxide is a very difficult to analyze because it has semi-metal behavior. Well, we are now ready to start making anti-reflection calculations where we will investigate different metals including copper, silver, gold, and aluminum, where we put a thin film of molybdenum oxide on a 100 nanometer thick layer of the metal, which is on a polycarbonate base. In fact, you can use any base you want, so I'm just using a polycarbonate, where this whole thing is embedded in air. And when we minimize the reflection, it's really the visible reflection that we are minimizing, where we use the photopic response as a weighting function of the eye. So we're using the eye's behavior to weight the reflection, and where we adjust the thickness of the molybdenum oxide layer to discover what the reflection minimum is. And we can see for many metals, reflection starts out with between 8 and 12% for low levels of oxygen, and a minimum is at around a stoichiometry of around 2.7. Well, we don't have to just depend on the target stoichiometry. We can make finer control of the we can optimize the anti-reflection by using the Brueggemann method. We can start in phase A with a number of different stoichiometries, phase B with stoichiometries of 2.9, 2.85, and so on. We can vary the volume fraction and see what happens. And now we can see that for copper, we're down around a 1% level. Well, those stoichiometries that we have discovered, I promised that we would look at the trajectory. All of those stoichiometries that we have optimized by using the Brueggemann effective medium approximation, they all fit on this line. And that's quite encouraging, because it tells me that we will have the chance of making a target of the optimized stoichiometry to produce these films. In conclusion, we have made molybdenum oxides in amorphous state over a wide range of composition. By measuring the reflection and the transmission, we have directly solved for their N and K, and that means we did not have to use any a priori dispersion function. These materials have negative band gaps, indicating that they have semi-metal behavior. And because of the semi-metal behavior, this is one reason why it will be difficult to fit these, because there's no known function, at least I don't know any function, dispersion function that has semi-metal behavior. One thing that is really important to understand is that because the effective medium approximations work so well, these materials truly are atomically mixed, and as we should expect. And finally, because these N and K fall on the trajectory that I mentioned, we can expect that these samples can be made by targets of specific composition. Thank you very much.